Hi everyone, it's Mr. Bowman. Welcome back. Now that we know how to use the inverse sine and the inverse cosine functions on our calculator and the limitations of those, we are going to use those to solve triangles. And when I say solve triangles, what I mean is you are given three pieces of information about the triangle, like an angle, another angle, and a side, and you're going to solve for the missing three pieces of information. So when we get done, we'll know the measures of all three sides and all three angles. And we're going to start out with something called the law of sines, which I'm going to prove for you in a minute. But before we do that, I want to remind you of the triangle congruence theorems from geometry. And if you don't remember, basically what those were is if we had, for example, two adjacent angles and a side, then we had the angle side situation, in which case we could prove two triangles were congruent to each other. And if you remember, corresponding parts of congruent triangles are congruent. If we had two angles and the side in between, we could prove two triangles are congruent. If we had two sides and the angle in between, then the triangles are congruent. Or if you had all three sides congruent, then you could prove that the two triangles were congruent. We're going to focus on these first three: angle, angle, side, angle, side, angle, and side, angle, side, because with these situations, in other words, if we know that information, we can use the law of sines to solve the triangles. And when we have those situations and we use the law of sines, we have one solution to the triangle. In other words, there's a unique set of angle and side measures for that triangle. We also have the triangle similarity theorem from geometry, which basically said if we have three angles congruent, three angles in one triangle congruent to the corresponding three angles in another triangle, the triangles are similar, not congruent, but similar. The best example of this that I can think of is think of equilateral triangles. All equilateral triangles are similar, but they're not all congruent. If we have this situation for solving triangles, then we have an infinite number of solutions. And if we have the side-side angle case, which is not a similarity theorem, the congruence theorem from geometry, you could not prove triangles congruent with side-side angle. But if we have that situation, we have what is called the ambiguous case. And when we have that, when we're solving triangles, we could have either 0, 1, or 2 solutions. And we will deal with that next time. Now you'll notice I didn't mention side, side, side. And the reason I didn't is because we're going to use something called the law of cosines to solve that situation. So the first thing I want to do now is to prove the law of sines. You will not be responsible for this, but I want to go through the proof anyway. So let's take triangle 1. And in triangle 1, we have the height drawn in, and as you know, the height is always perpendicular to the base. So we could say that the sine of angle A is equal to the opposite h over the hypotenuse b. But we could also say in that same triangle that the sine of angle B is equal to the opposite h over A. If we were to solve both of those equations for h, we would get h is equal to B sine A, and h is equal to A sine B. In which case we could set those equal to each other. So we would have B sine A is equal to A sine B. And we could then divide both sides by A and both sides by B. and you would see that the A's would cancel out on the right-hand side and the B's would cancel out on the left-hand side, and we have the sine of angle A over side A is equal to the sine of angle B over side B, which we can extend and say is equal to the sine of angle C over side C. And that is the law of sines. We can also write that by taking the reciprocal of all three parts. So we could write it as A over sine A is equal to B over sine B is equal to C over sine of C. So those are the two variations of the law of sines. In triangle 2, we can also prove the law of sines. And in triangle 2, the reason we're doing that there is because we have what we call an obtuse triangle. One of the angles is between 90 and 180 degrees. And in the first triangle, it's an acute triangle. So we want to convince you that it works for all triangles. So in triangle 2, we have the following. We have the sine of angle B is equal to H over A. And just to be clear, when I say angle B, I'm referring to this angle B right there. And we also have the sine of angle A is equal to H over B, which you will see is exactly the same as above. Now, what you might be thinking about this is that angle B that I showed you is not inside the triangle. Well, it turns out that this angle B inside the triangle, which I'm going to mark right now, has a measure equal to 180 degrees minus the angle B that I first showed you. And if you think about that, basically, if you take the sine of an angle in the first quadrant, an angle that has a measure between 0 and 90 degrees, the supplement of that, the sine of the supplement of that, has the same sign. It would be an angle in the second quadrant. So we can go through this whole process again and solve for H and set the two equations equal to each other, and we will get the law of sines all over again. So we have proven the law of sines for both an acute and an obtuse triangle. Now we're going to apply that to some problems. So I want to remind everybody how triangles are labeled before we go any further. Angles are measured with uppercase letters and sides with lowercase letters, and the side that has the same letter as the corresponding angle is across from that angle. So in other words, in this example number 1, angle A of 36 degrees is across from side A, which has a measure of 8. So we're going to start out by sketching some random triangle here, and we are going to label it. So A, B, C, uppercase letters for angles. Angle A has a measure of 36 degrees, angle B a measure of 48 degrees, and angle C we could find by taking the property that the sum of the angles in a triangle is equal to 180. So 180 minus 36 degrees minus 48 degrees is equal to 96 degrees. So angle C is 96 degrees. You will notice my triangle is not drawn to scale. Side A is equal to 8, so A is equal to 8. And I want to go back for a minute. We had the following situation. We had angle A, angle B, and side A. So we had the angle, side situation. And the reason I point that out is because on the first page of the notes, I had mentioned that situation is when you can use the law of sines and you will have a single solution. So if you remember that, it's going to help you know which method to use to solve the triangles. So angle, side, angle, and side, angle, side. You should use the law of sines to solve those, and those will have one solution. What you want to watch out for is when you have side, 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 you can't use the law of sines. Or if you have side, side angle, you can use the law of sines, but you might have no solutions, one solution, or two solutions. So now that we have this information here, we are going to solve for the missing information. So side C and side B. And my recommendation would be to solve for the side B first. That being said, you could solve for side C first if you like to. So let's set this up. Since you can write the law of sines either with the side on top in the numerator or the side on the bottom, since we're solving for the side in this situation, I like to write it on top because it makes solving easier. So I'm going to write B over the sine of angle B, which is for the sine of 48 degrees, is equal to, now you want to pick a combination of sides and angles that you know. So we're going to use 8, which is side A, over the sine of angle A, which is 36 degrees. And then we're going to solve that by multiplying both sides by the sine of 48 degrees. Sine of 48 degrees. So those cancel on the left-hand side, and we get our answer on the right-hand side. You, as much as possible, save the rounding until the end. So if you make sure your calculator is in degree mode and you go ahead and solve this, you will get B is approximately equal to 10.11. Now you want to set this up to solve for C, so we're going to do the same thing. C over the sine of angle C, which is 96 degrees, is equal to 8 over the sine of 36 degrees. Multiply both sides by the sine of 96 degrees and solve that, and you will get side C is approximately equal to 13.54. Notice I did not use my rounded answer for side B to solve for side C in that situation, and I left all rounding to the end. The last thing I encourage you to do is check to make sure that your answers make sense. So side C is approximately 13.54. Side B is approximately 10.11. And as you recall from geometry, the smallest side should be across from the smallest angle, and the largest side across from the largest angle. And that is true. Another thing that you can do is check the triangle inequality theorem, which basically says that if you add any two sides, they have to be greater than the third side. And you can verify that in this situation. So in this next problem, you'll notice that we have much of the same information. We have angle C is 96 degrees. Angle B is 48 degrees, and side A is equal to 8. So the same information we came to find in the first problem, but let's draw a picture of this first and see which of the triangle congruence situations we have. So we have angle A, angle B, angle C, again, not drawn to scale. Angle C, 96 degrees. Angle B, 48 degrees. And side A is equal to 8. So we have the side angle side situation. And we can go through and we can solve that using the law of sines, and you are guaranteed one solution. So I encourage you to go through and solve for angle A, side B, and side C, and verify that you get the same numbers as the problem above. The only point in doing this example is to show you that solving triangles with a side angle side situation can be done using the law of sines. In problem number 3, we are going to draw our triangle again, and we are going to label it. So A, B, C. Angle A is 26.3 degrees. side A is equal to 7, side B is equal to 6, and you'll notice here that we have two sides and the angle not between them. So this is the side-side angle situation. This is the ambiguous case. And again, there could be no solutions, there could be one solution, there could be two solutions. And that's why it's called the ambiguous case. We will delve into that in the next lesson. So let's take a look at the next problem. Triangle number 4. In this particular triangle, we have the following information. Let's label our triangle. Again, A, B, C, probably not drawn to scale. A is equal to 7, B is equal to 6, and C is equal to 11.9. This is the side, side, side situation. So side, 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 you will notice that I did not include that as one of the methods to use the law of sines for. So we're going to put a note here, can't use law of sines to solve. Must use what we're going to call the law of cosines, which we will talk about later on. The only situation where you could solve this, if you have the side, side, side situation, is if it is a right triangle, and you can verify that by seeing if a squared plus b squared is equal to c squared, and you will see that it's not, so it's not a right triangle, so you cannot solve that. Let's take a look at the last situation. The last situation here, which we will draw angle A, angle B, angle C. Angle A is 26.3 degrees, angle B is 22.3 degrees, and angle C is 131.4 degrees. Again, not drawn to scale. This is the angle, angle, angle situation, and there are infinite solutions to this. In other words, if I had you draw a triangle that had these angles, then you can have an infinite number of combinations of sides, so we don't bother solving them. So the last thing I want to do here is I want to use the law of sines for an application problem. So here's the situation. Forest Ranger Chris Johnson at Ranger Station A, lower left of our triangle, sights a fire in a direction of 32 degrees east of north. So what that means is if you look straight north and then you rotate to the east 32 degrees, that's the direction of the fire. So the fire is at point C on the triangle. Ranger Rick Thorpe at Ranger Station B, lower right of our triangle, 10 miles due or straight east of A, sights the same fire on a line 48 degrees west of north. So Ranger Rick looks north, and then he turns to the west 48 degrees and sees the fire at C. Find the distance from each ranger station to the fire. So what we want to do is we want to find the length of side A and the length of side B. So let's think about what we have here for our triangle ABC. Well, it looks like all we have is side, but that's not the case. What we have is we know that 32 degrees is the complement of the angle that I just drew in red there. So 32 plus 58 degrees gives us 90 degrees. And angle B inside our triangle is the complement of the 48 degree angle. So angle B has a measure of 42 degrees. So we have an angle side angle situation which we can use the law of sines to solve for. So what I would like you to do is I'd like you to pause the video, set up the law of sines to solve for side A and side B. Go ahead and solve those, And then when you're done, hit play on the video and verify that you got the right answers. All right, so the first thing that you have to do to solve this triangle, to solve for sides A and B, is find the measure of angle C in triangle ABC. And to do that, we use the two right triangles and the fact that the sum of the angles in a triangle is equal to 180. So we have the 58-degree angle and the 90-degree angle, and to that, if we add 32 degrees, we will have 180 in the triangle on the left, the right triangle on the left. And the right triangle on the right, if we add 42 to 90 and another 48 to that, we will have 180 degrees in that triangle. So angle C that we are interested in is 32 degrees plus 48 degrees. We then set up to solve for side A or side B. So side A over the sine of angle A is equal to side C over the sine of angle B. Solve that, you get A is approximately 8.6 miles. Do the same thing for side B. B over the sine of 42 degrees is equal to 10 over the sine of 80 degrees, and B is approximately 6.8 miles. Again, I would encourage you to verify that the largest side is across from the largest angle and the smallest side across from the smallest angle, and that the sum of any two sides is greater than the third, which you can see is true in this case. So we're going to stop there for today. Next time we will talk about how to deal with the side-side angle or the ambiguous case to solve triangles using the law of sines.